Okay, so hello everyone. My name is Zhongzhen. It's a great honor to share our work with you. I will briefly introduce our whole framework and the training pipeline. I hope our work would provide some helpful insights for you. As we know that previous segmentation work can be divided into two types. One is the textual prompted method. It utilizes textual representations to guide the segmentation task to guide the segmentation process, and it requires the alignment between textual and the visual representations. But as we know that long-term distribution in medical domain, its phenomenon would hinder the effective learning of the alignment because visual text paired data is limited. And on the other hand, visual prompts provide a more intuitive and direct method to enhance the segmentation process but fail to convey the general concept of each object, leading to a performance drop. For example, if we only provide one point, this point cannot identify all attributes of the target tumors. So based on this, Uh, we propose CAT. CAT means coordinating anatomical and textual prompts. CAT adopts a dual perspective prompting schema. It employs the cropped volumes and enhance the textual prompts for segmentation process. Our CAT consists of three main modules: visual backbone, shell refiner, and prompt refer. The the visual backbone consists of visual encoder and the visual decoder. The visual encoder responsible for extracting multi-scale visual features, and the visual decoder upsamples the visual features into a high-resolution pixel map. These maps are then used for the final mask prediction. And in our in our implementation, the visual backbone adopts the swing unit architecture, and it is also initialized by its provided pretrain rate. For anatomical prompts, we leverage the bounding box derived from the masks to crop a set of prompt volumes for each category, and these volumes are then resized into a uniform shape. For the textual prompts, we utilize their large language models to generate descriptions with medical domain knowledge. It should note that those types of prompts are constructed and embedded offline to reduce the training overhead. And as it can be seen in our figure, our module takes in two types of queries, segmentation queries QS and prompt queries QA and QT. QA means anatomical queries and QT means textual queries. And these are then passed into the shell refiner. In the shell refiner, these queries interact with visual features for further updating. The output of the shell refiner are then passed into the prompt refer. In the prompt refer, the segmentation queries attend to those types of prompt queries to obtain the relevant context. And then the output of the prompt refer will be used for the final mask prediction. And we also incorporate query level contrastive learning to enrich the feature representation. Okay. And then I will introduce the details of how to train our model. Our code are available on GitHub. And to train our model, you need to download the dataset and use the code to convert MPZ files into organized NII files. And then we should transform and extract the valid labels with our code. And the third step is optional. It is the process of constructing anatomical prompts. And then we should we should transform and normalize the labels from different datasets into a unified form. It should note that this step could take some time, and we utilize the cache dataset to store the results of data pre-processing. And you should set a value to load the pre-processed data into memory during training based on the size of CPU memory. We will also provide code in the data loader to cache the pre-processing results to the disk, which can be used to replace the original code. Okay. In the final, there are some suggestions for how to improve the results. In our baseline, the textual encoder are frozen, so the textual encoder can be further trained to enhance the performance. And we also think that more powerful visual backbones can be employed to improve visual feature extraction. And in the experiment, we observed a domain gap exists between the pre-trained weight and the target dataset, which means that we can choose more powerful pre-trained weights to construct and embed an anatomical prompt. It is also beneficial to rebalance the data distribution, such as modalities, categories, and anatomical regions. And you can also apply some metrics to process normal and abnormal classes, such as design masks in the prompt refer to tailor representation learning accordingly. Okay, that's all. Thank you. If you have any questions, please email to me.